In section 10.2, we're going to take section 10.1, which either served as a review or maybe an introduction to parametric equations, and extend that now to calculus and the concepts related to calculus. So just kind of keep in mind some of the things you saw in 10.1 regarding the basics of parametric equations, and ultimately these calculus concepts that we're going to apply to these parametric equations should feel very natural compared to all the experiences and problems you were solving earlier in this class. So now we're ready to take those parametric equations and apply some of the calculus concepts to them. And in this case, we're going to be looking at the derivative of parametric equations. So to kind of build up to that concept, here's the question we're trying to answer. What makes a path smooth? Of course, graphs like this parabola here can be smooth. Other graphs can, of course, be, for the lack of a better word, spiky. I guess what we're really talking about are these sharp corners or cusps right here. Either way, when we're trying to think about these parametric graphs and asking the question, how can they be smooth or spiky, really what we need to look at is the derivative of both of the separate equations. A parametric set of equations will have a smooth path if dx dt and dy dt are both continuous and not zero at the same time. So be careful with these two derivatives here. dy dx, which we've been studying all up until this point in this class, was what we call the derivative. It was the slope of a function. But what we're talking about here is that we're taking the derivative of x with respect to time and the derivative of y with respect to time. Those two technically are not dy dx. We'll talk about dy dx in a moment. So let's go ahead and apply what we see here to this example. And we actually did this example in 10.1, where we eliminated the parameter and graphed the set of parametric equations. But here, we're asking the question, will this produce a spiky or maybe a cusp on our graph? What we need to do then is to take the derivative of both of these separately. dx dt, the derivative of our x equation with respect to time, is a nice easy derivative. Don't overthink that. It's just 3t squared. dy dt, on the other hand, is just the derivative of our y equation with respect to time. Again, don't overthink that. That's just 2t. We need to figure out if both of these derivatives are simultaneously zero. So we need to set both of them equal to 0. 3t squared equals 0, of course we get t equals 0. 2t equals 0, we also get t equals 0. So based on these conditions up here, we can't have simultaneous zeros for dx dt and dy dt. As it turns out, we're getting a derivative simultaneously being 0 at t equals 0. So what that's telling us is that we're going to have some sort of sharp corner, spike, cusp, however you want to refer to it, at t equals 0. And we kind of already know that. If you refer back to the notes in 10.1, we did the whole process of eliminating the parameter and got the equation y equals x to the 2/3. And when you graph that, you can clearly see that sharp corner right there as that finger kind of is discovering at t equals 0. So that's kind of one of the first ideas that we kind of need to think about when we're dealing with derivatives concerning parametric equations. But I think bottom line is we're really concerned with finding dy dx. And again, keep in mind, we don't have an equation in terms of y's and x's here. We have two equations with x and y and t. So there's got to be some way for us to find what I guess I'll call regular slope dy dx. And as it turns out, it's a little bit of a formula that you're going to have to know. And it's a very intuitive formula on top of that. dy dx is dy dt over dx dt. And that should almost in a way be common sense, hopefully, in a mathematical sense. dy dx is slope. It's a rate of change. And you can see here dy dt is what we could call our change of y. In the bottom of this fraction, we have dx dt, which we could call our change in x. So at least this formula, if you want to call it that, is a very intuitive kind of formula, assuming you still remember the most important concept concerning derivatives, and that is a slope, or a change of y, or over a change of x. So if we want to practice using this, we're going to take a look at this example. I want to find dy dx for this problem, not dx dt, not dy dt, but we're looking for dy dx for this problem. So what we need to do is to take both of these derivatives of these parametric equations. Dx dt, luckily, is nice and easy here. That's just e to the t. The derivative of an exponential function, if it has a plane power, is itself. Dy dt, on the other hand, is going to require the chain rule. The constant of 3 we're just going to leave in the front. E to the 2t becomes e to the 2t. And because of the chain rule, we have to multiply by u prime, and the derivative of 2t is just 2, and we can clean that up to be just 6 e to the 2t. If we want to find dy dx, we need to take dy dt, which is the 6e to the 2t, and divide that by dx dt, which is e to the t. If we simplify that, e to the 2t over e to the t would just be e to the t. We would take the powers and subtract them, so 2t minus t would just be 1t. And that's the result. The derivative of these parametric equations, dy dx, is 6e to the t. As an alternate way of looking at this, and just to kind of verify and show you that this math works out in a sense either way, if you recall, when we eliminated the parameter back in 10.1 on this particular set of parametric equations, we found that that equation was y equals 3x squared. And you can see we could take the derivative of that instead. And we know that derivative. We know the derivative is 6x. So that's not quite matching our derivative we got with our parametric equation formula. But if you realize an x is really e to the t, then it will match. If we take dy dx equals 6e to the t and replace that e to the t with an x, those two end up matching. So as it turns out, you can get this derivative either way, but I'm sure you can imagine in a lot of problems, going through the eliminating the parameter process and then taking that derivative would probably be harder than just go ahead and using this formula right here. Okay, so let's just apply this concept of finding a derivative of a parametric equation to these next couple examples. In this problem, we want to find dy dx and any horizontal or vertical tangent lines. So we have our set of parametric equations here. I'm going to go ahead and just graph this for us so we can kind of in a sense cheat and see what the answers might be here, but also to kind of tie our answers to a visual. If you take these parametric equations and graph them, you'll get this shape. And just to kind of give you the sense or the flow of this graph, at t equals 0, we're at the origin. If we pick negative times, we'll be up here at the top, and if we pick positive times, we'll be down here at the bottom. So as it turns out, our graph is kind of following this shape as we start at the beginning, so to speak, and kind of continue as time gets from negative to positive. So if we can put arrows there, that'll kind of show that flow of how that graph gets traced out. But either way, we're not really so concerned about that. We just want to figure out what dy dx is and where we have horizontal and vertical tangents. And you can actually see those horizontal and vertical tangents in the picture, but let's go ahead and find dy dx first. To find dy dx, the derivative of y with respect to x, we need to take the derivative of the x equation with respect to time, and we need to take the derivative of the y equation with respect to time. Luckily, both of those are very simple to do. And now we can apply the formula from the last slide. Dy dx is dy dt over dx dt, the change of y over the change of x. And when we plug that in, that's it. Our derivative is 3t squared minus 3 over 2t. To find horizontal and vertical tangents, all we need to do is set each of the proper components equal to 0. We're going to have horizontal tangents when our dy dt is equal to 0. If we set that equal to 0 and solve, we'll factor out the 3. we have a difference of squares, so we get two values of t where we have horizontal tangents. And you can actually see that up in the picture. At t equals -1, you can clearly see a horizontal tangent, and at t equals 1, we can clearly see a horizontal tangent. But let's pretend we didn't actually have the graph here. What if we wanted to know what point that happens at? Every problem is a little different. Sometimes you'll be asked to find the time where a tangent line is, or maybe you'll be asked to find the point where that tangent line is, like we're typically used to in previous questions. If you want to find the point where t is equal to -1, all we need to do is take these points here, or these times I should say, of -1 and 1, and plug them into our two parametric equations. When we plug in -1 into x, we'll get +1, and we plug in -1 into y, we'll get 2. So that's at the point 1, 2. If we take t equals 1 and plug it into our formulas, or to our equations I should say above, we'll get our x coordinate to be 1, and we'll get our y coordinate to be -2. Again, you can clearly see that in the pictures above, so I'll go ahead and draw those horizontal tangents in for illustration. So if the horizontal tangent is setting the y component equal to 0, logically speaking then, the vertical tangent then would occur when the x component is equal to 0. And when I say x component, I mean the derivative of the x. So dx dt would have to be equal to 0. Here, luckily, that's nice and quick and easy. When we set 2t equals 0, we get t is equal to 0. And again, you can clearly see that in the picture. But presuming we didn't have a picture, of course, if you wanted to know the point at which we had a vertical tangent, then we would take that t value and plug it into our two equations above to get our x and y. When we plug in 0 into x and y, we both get 0 on both of those, and again, clearly you can see that the origin 0, 0 produced our vertical tangent line, or an undefined slope. So again, we're just kind of still applying all these concepts from way earlier in this class, now to just a different point of view, so to speak, with these parametric equations. Here we have an AP test multiple choice question, and they're telling us that there's a curve C defined by these parametric equations right here. We want to figure out which of the following is an equation of a line tangent to the graph of C at this point right here. So I guess the first thing we need to do is to find the derivative of y with respect to x, which requires us to take the derivative of our two parametric equations separately. Luckily, this is very straightforward. I guess the only thing I would say watch out for is make sure you put the dy dt in the top, which is 3t squared, and put the dx dt in the bottom. In this case, that's 2t minus 4. We're trying to figure out which of the following is an equation of a line tangent to the graph at the point -3, 8. So we need to find the slope so we can write that tangent line equation. If we take our x and y and plug in, we should be able to do that. So how are we going to figure out how to do this? You'll notice our derivative over here doesn't have x's and y's in it like you're used to seeing. Way back when we first studied this in chapter 2, our derivative of course only had x's, or maybe it had a y in it, but really that's all it had. Since we need to figure out the t at the point in question, we need to take that point and solve for t. Now I guess there's one of two ways we can do this. We could always take the -3 and plug it in for x and solve for t, but that equation, while not hard, is going to require a lot more work. Luckily, our y equation is very straightforward. So if we use the y equation to find the t, that'll probably be a little more efficient in terms of the work we have to do. So we know at the point that we're looking at, our y value is 8. And that's equal to t cubed. So if we take the cubic root of both sides, we'll find our t to be 2, and now we can plug that into our derivative equation. If we plug in 2, we'll get a slope of 12 over 0. And if we get a slope of 12 over 0, we know that slope is undefined. So then what would an equation of a tangent line look like for an undefined slope? Well, if you think back above here for this equation of a tangent line in this first example where we had a vertical tangent, what is the equation of a vertical line? And specifically, what is the equation of a vertical line at the point where we're looking at our tangent line? If you recall, the equation of a vertical line is just x equals the point in question. And since we're looking at the point -3, 8, our vertical tangent line must be at that point -3, 8. And that must have an equation of x equals -3. So if we can find the first derivative of parametric equations, of course, by extension of that, we can find the second derivative of parametric equations. And luckily, that's actually where we'll stop. We don't have to worry about third derivatives and fourth derivatives and so on. But there is a bit of a more involved process in finding the second derivative of parametric equations. So rather than talking about the details of this formula, I'm going to break down the steps of using this formula into these 3 steps. But just kind of realize, based on this formula, at some point we're going to need dy dx. So we're going to need that formula from the first slide of dy dt over dx dt. So let's go ahead and go through this example to see if we can figure out what the second derivative of these parametric equations are. The first step is to find dy dx. To find dy dx, we need to take dy dt and dx dt and divide them. Again, luckily these are very straightforward. These are simple derivatives, so don't overthink them. When you take those 2 derivatives and plug them in, we'll get a fraction. The first step was to find dy dx, and we just found it. So I guess you can look at this as maybe another example of just finding the derivative of y with respect to x when you're doing parametric equations. But now we want to keep on going. We want to find what the second derivative is. And you'll notice in the top of this formula, we need to take the derivative with respect to time of our slope machine dy dx. And that kind of makes sense. If we're taking a second derivative, we need to take 2 derivatives, except we're kind of doing it a little different than we've done in the past, of course. So the second step now is to take the derivative of dy dx, but now with respect to t, because all we have in our derivative are t's. So we're taking the derivative of our derivative with respect to t. And you'll notice we're taking the derivative of a quotient, so that's going to require the quotient rule. Without going over all the steps of low d high minus high d low over low low, I'll let you try that if you want to do it on the side and just verify that you get this for the practice. I'm going to skip all that and just jump straight to the result. After we have that, the last step is just plugging everything in. We need to take this result from step 2, which again was the derivative with respect to t of dy dx, and then divide that by dx dt. And really that's just a matter of plugging those things in. So the answer from step 2 gets put in the top of the fraction, and then we divide by dx dt, which we found previously in the problem up here. After that, it's just a matter of cleaning that up and making it look a little bit nicer. When you have a fraction in the top of an overall fraction, this top denominator goes to the bottom of the overall fraction. And if that happens, we'll have 1 minus 2t squared times 1 minus 2t, or 1 minus 2t cubed. So with that, we've come to the end of finding the second derivative. Again, a little more involved than finding the first derivative, but it's still a formula, and it's, I guess, after that, a process if you just break down the steps of the formula. Okay, so remember, this section is called Parametric Equations and Calculus, so we're going to kind of jump around a bit in terms of the calculus concepts as they apply to parametric equations, because now we're going to take a look at a totally different subject than the derivatives we were looking at before, and that is arc length. If you want to pause the video at some point throughout this and go back to 7.4 and do a quick little review of arc length, that may or may not be helpful, but just as a quick vocabulary definition review, arc length, again recall, is just the length of a curve. And back from 7.4, when we're dealing with regular equations in rectangular form, in other words, y equals equations, we were using this formula again back in 7.4. But now we're dealing with parametric equations. The process of developing this formula that you're about to see is very similar to the one that we did back in 7.4 for rectangular equations, or again, the regular y equals equations. So what we're doing here is we're taking a curve and we're zooming in very, very close. And what we're trying to do is find the length of this curve right here. Of course, we don't know how to do that, but if you think about this being a very, very, very tiny, a super duper tiny little piece of this graph, then this little line L, which would be an approximation, so to speak, if we took an infinite amount of those and added them up, that would eventually give us our exact value for the length of the curve. And that's kind of what we talked about back in 7.4. But here we have two different components contributing to our arc length, or to the length of the curve. That's going to be a little component of x in the horizontal direction, which will of course be dx dt, and then that other component will be a little change of y in the y direction, or a dy dt. Bottom line is, just like in 7.4, to develop this formula for arc length, we're just going to apply the Pythagorean theorem. If we wanted to find how long L was, we would square the two legs of this right triangle, and then add them, and then take the square root. The length of this line segment L, which is a very, very, very tiny little line segment, is given by this equation. And again, if we would want to find the exact length of this curve, we would want to add up an infinite amount of these little line segments. The tool that we have in calculus that lets us add up an infinite amount of things is, of course, the integral. So for arc length in the parametric form, it looks very similar to the arc length in the regular form, if you want to call it that. The difference here is we're going to take dx dt, square it, we're going to take dy dt, square it, and then take that square root as we take the integral from a to b. So when computing the arc length for parametric equations, the integration is with respect to the parameter. Be careful, don't take the derivative dy dx and put it here. All we're doing is taking the derivative of each of the equations x and y with respect to t. So to illustrate this, let's take a look at an example. We want to only set up the integral that computes the length of the path described by the parametric equations. So of course, another way of saying that is arc length. The parametric equations we're looking at are cosine cubed and sine cubed, and we want to find the length of this curve from 0 to pi over 2 in terms of t. So the one extra little point I need to make here is I'm actually going to do this entire problem and actually find the length. This AP test question only wanted the setup, but as it turns out, we can actually complete the entire problem without it getting too messy, and it's probably a good exercise in actually doing the entire problem, because you never know if you might actually have to compute the actual arc length rather than setting it up. Okay, so the first thing we can do, of course, is set up the integral. That's very straightforward. We're going to set up an integral from 0 to pi over 2. I'm going to kind of do all the side work to fill in this formula over here. It's probably a bad idea to kind of do all your work in the formula itself, because that can get really messy, but that's kind of up to you the way you approach these problems. So we need to find dx dt and dy dt. For dx dt, just realize, and this is kind of a skill we haven't seen for a while, but certainly it goes back to chapter 2, the best way to write our trig functions to a power is with parentheses. So I'm going to take cosine cubed t and write it as cosine t all in parentheses to the third power, so that we can realize when we're taking the derivative, this is an application of the chain rule. We don't have a plain t, so to speak, to a power, so we're going to have to apply the chain rule. So we'll bring down the power of 3, leave that u alone, reduce the power by 1, and then multiply by u prime. The derivative of cosine t is, of course, negative sine t. If we clean that up a little bit and square it, we'll end up with this value. 9 cosine t to the 4th times sine t squared. That negative, of course, would go away when you square it. 3 becomes 9. And then, of course, when you square cosine squared, it becomes cosine to the 4th. And when you square sine, it becomes sine squared. Same process goes for the y component. We're going to rewrite that sine cubed as sine parentheses to the third power, and then go ahead and apply the chain rule just like we did above. We'll bring the power down, leave that u alone, reduce the power by 1, and then multiply by u prime, and in this case the derivative of sine is cosine. Again, we want to square dx dt and dy dt. So when we square that, we'll end up with 9 sine to the 4th cosine squared. Once you do all that side work, again, I think it's a good idea to leave that all on the side so that now we can take those two results and plug them in. And that actually turned out to be the final answer in terms of this particular question. But like I was mentioning before, as a good exercise to go through, especially in a problem like this where we can complete the problem by hand, that's what we're going to go ahead and do. So let's go ahead and proceed with this problem and actually find the arc length itself. You'll notice that both of these terms have a 9, a sine squared, and a cosine squared in common. So when you factor that out of the first term, all you're left with is cosine squared. When you factor the common factor out of the second term, all you're left with is sine squared. And the reason this problem works out very nice to do by hand is, of course, this cosine squared plus sine squared, if you remember your Pythagorean identity, is just equal to 1. So really we're taking the square root of 9 sine squared cosine squared. And if we apply that square root to all three of those pieces, we'll end up with 3 sine times cosine. So how do we approach this integral? Well, one of the keys to identifying how to take an integral is there a u substitution that would help you do the integral? And as it turns out, we can choose u to be sine, because the derivative of it is cosine. And that would make our u substitution work out very nicely. Sine goes away and becomes u. Cosine t dt all goes away and becomes du. After that, I'm kind of running out of space here, so I'm going to kind of skip a step or two here. But when we find the integral, we'll add 1 to the power and divide by that new power. So we'll end up with 3u squared over 2. Or if we rearrange that a little bit, we'll end up with 3 halves sine squared when we plug the u back in. And here's where I'm going to have to skip some steps here. When you plug in the top bound of pi over 2, and when you plug in the bottom bound of 0, and subtract those two values, you'll end up with 3 over 2 as the length of the curve from 0 to pi over 2. Okay, the last major calculus concept that we're going to have to tackle here concerning parametric equations will take us back to those two topics at the end of Chapter 2 and Chapter 4 concerning position, velocity, and acceleration. So if we're given two parametric equations, x and y, and the x equation we're just calling the function f, and the y equation we're just calling the function g, then we can define a bunch of things from the point of view, again, of position, velocity, and acceleration. The way we define these things is with what are called vectors. Vectors are just fancy ways of saying that we have two different components, in a sense, to the motion, or to the movement of a certain object. So instead of just position, where in the past we wrote position as just x of t, and that's all position was, now we have these two components to position. We have the x component, which we're calling f of t, and we have the y component, which we're calling g of t. The way we define our position vector is with these little bent parentheses. That's not a typo. They're not supposed to be nice curved parentheses. They're what I guess we could call a bent parentheses. So again, really nothing different than what we've seen before, but again, there's two components to our position, an x and a y, and we define that as a vector. And again, we're talking about position, so that would be called a position vector. Of course, if we took the derivative of the x equation, which is position, that would be velocity. The derivative of position is velocity, so dx dt would not be just the overall velocity, it would be the velocity in just the vertical direction. If we took the derivative of the y equation, that wouldn't be the overall velocity, that would just be the velocity in the horizontal direction, the y component, so to speak. To kind of follow that up with the velocity vector, if we have a position vector and we want to find the velocity vector, all we need to do is take the derivative. And it's the same notation. Again, the reason we have to write this as a so-called vector is because there's two components to this motion. The dx dt component of motion, which is in the vertical direction, and the dy dt component, which is in the horizontal direction of movement. After that, we can kind of look at some of the things we studied way back in Chapter 4 at the end of Chapter 4. So if you, again, need a reminder of this, look back at 4.7. But you'll recall that if we integrate from one time to another time of v of t dt, hopefully you still remember this formula, that gave us the position at t2 minus the position at t1. Hopefully that's still in a formula and an idea that you recall. But here, again, we're trying to apply this concept to parametric equations. So if we integrate our velocity in the x direction, or the vertical direction in a sense, then that's going to give us the position at t2 minus the position at t1. But of course, we have two components to motion here. So if we integrate the y component from one time to another time, t1 to t2, then that'll give us the y position at time 2 minus the y position at time 1. So if you're feeling like some of this is a little foreign and not as clear as it used to be, again, you might want to review some of these ideas so that you can apply them more smoothly to now these parametric equations, and going back and looking at 4.7. Luckily, once you kind of put all this stuff together, the acceleration vector makes perfect sense. If you have a velocity vector and you want to find the acceleration vector, of course you'll just take the second derivative of x, you'll take the second derivative of the y equation with respect to t, and that'll give you your acceleration vector. After that, there's just a couple more little formulas that you have to know before we look at some examples. To find speed within this parametric world, we're going to take the square root of dx dt squared plus dy dt squared. So that looks a little bit like the arc length formula without the integral part. So then, if we want to find total distance, that's actually the same thing as finding arc length. If you imagine graphing in a sense and following the path of that curve, then of course the length of that curve would be the total distance traveled. So luckily, arc length and distance traveled are the same exact formula, but just don't make the mistake of mixing up speed with the distance formula, since they're very similar. One has an integral, one doesn't. Okay, so this topic of velocity vectors, position vectors, all that stuff as it pertains to parametric equations is a pretty big subject on the AP BC test. So the rest of these slides are going to be dedicated to applying those concepts to these free response questions. These are usually calculator allowed questions, not always, but just kind of keep that in mind that this is a calculator allowed question as we move through this free response question. So we have an object moving along a curve in the xy plane, and they tell us there's a velocity vector x comma y. The dx dt equation is sine t cubed. The dy dt equation is cosine t squared. So you'll notice they're not giving us the position equation, x and y. They're giving us the velocity for x and the velocity for y. They also tell us at t equals 2, the object is at the point 1, 4. And again, this would be an x, this would be a y. So at t equals 2, we're at the point 1, 4. Part A wants us to find the velocity and acceleration vectors at t equals 2. Luckily, the velocity vector is kind of ready to go. We know the velocity vector is dx dt comma dy dt, so we just need to take both of those and put them in our bent parentheses. We want to find the velocity vector at t equals 2, so we'll plug the t of 2 in, and if we clean that up a little bit, we'll get sine of 8 comma cosine 4. It's perfectly acceptable to leave exact answers on the AP free response questions rather than getting a decimal. To find the acceleration vector, we just need to take the derivative of the dx dt on its own and the dy dt on its own. And here that's just going to require that you recognize a little bit of a chain rule application. We're taking the derivative of sine of stuff, so that's going to be an application again of the chain rule. The derivative of sine is cosine, and then we'll put the t cubed, but then we need to multiply by u prime. This 3t squared right here is our u prime. The derivative of t cubed is 3t squared. When we take the derivative of cosine t squared, again an application of the chain rule, the derivative of cosine is negative sine t squared, but then we need to multiply, since we don't have a plain t on the inside, u prime, and that is in this case 2t. Once you write that out, that is our velocity vector, and they want us to figure out the velocity vector at t equals 2. So we'll take the value of 2 and plug it in for t. Once you clean that up, we'll get 12 cosine 8 for the x component, and we'll get negative 4 sine 4 for the y component. Again, you could find the decimal here, but there really is no point. You can just leave it as an exact answer. Part B of this free response wants us to find the slope of the tangent line at the point where t is equal to 2. Luckily, we did a problem just like this before in this lesson. To find slope, dy dx. Careful, they want us to find slope. So that's not dx dt, that's not dy dt, that's dy dx. That's just an application of the formula we saw at the beginning of this lesson. Dy dt over dx dt. And luckily here, they give us both of those things. We need to find the slope at t equals 2, so we'll take 2 and plug it in, and we'll get a value of cosine 4 over sine 8. Again, leaving it as an exact answer like that is perfectly acceptable. The last question, and I think probably the most important question in a sense, is to find position. The reason, in a sense, that's the most important question is just realize there's no way to integrate sine of t cubed and cosine of t squared by hand. There are no antiderivatives for those for what we know right now. So we need to take the alternate approach like we saw back in chapter 4 or 4.7, where we use the fundamental theorem of calculus as a formula. Luckily, you saw that formula on the previous slide. So you'll notice we want to find the position of the particle at time 1. They tell us the position of the particle at t equals 2 is again 1, 4. This is our x, this is our y at that time. So at t equals 2, x is 1, at t equals 2, y is 4. The reason that plays a part before we can set up this formula is we need to know what bounds we're integrating from. And of course you can see we're trying to find the position at time equals 1. They tell us the position at time equals 2, so those are going to be our bounds. And since we're dealing with with parametric equations, we have two different problems we need to do. We need to find the x position, and we need to find the y position. So we're going to do the x position first. We're going to integrate from 1 to 2, dx dt dt. If we do that, that'll give us the position at 2 minus the position of x at 1. So we know the position at time 2 is 1. So that we can easily plug in without any issue. dx dt, again from above, is sine t cubed. X position at 2 is 1. And then we're trying to find, of course, the position at time equals 1. If we take the TI-89 and evaluate that integral, we'll get 0.218. And if we take that 1 and subtract it, and then also move that negative over, we'll find that the x-coordinate at t equals 1 is 0.782. But of course, position involves an x and a y value. So to find that y value, it's essentially the same process, except we're now going to use the y components that we're dealing with. So we're going to integrate dy dt from 1 to 2, and that would give us the y position at time 2 minus the y position at time 1. If we take y2 and plug that in, which would be 4 up here, we'll be ready to go. So of course, dy dt from above is cosine t squared, and we'll use the TI-89 to figure out that value. y2 again from above is 4, and then of course we're trying to figure out what the position of y is at t equals 1. If we take that information and plug it into the calculator, we'll get negative 0.443 equals 4 minus the position of y at 1. If we subtract 4 and move that negative over, we'll find that the y point, or the y coordinate, at t equals 1 is 4.443. Okay, so hopefully that last free response example gave you a good idea of how we're going to apply this whole idea of parametric equations in calculus to the previously learned concepts of position, velocity, and acceleration. So here we have one more AP test free response question on these next two slides, and in this particular situation we're dealing with a diver leaping from the edge of a diving platform into the pool below. The figure right here, not the animation, but the figure shows the initial position of the diver and her position at a later time. At time t seconds after she leaps, the horizontal distance from the front edge of the platform to the diver's shoulders is given by x of t. And that makes sense. X component is always the horizontal direction. And the vertical distance from the water surface to her shoulders is given by y of t. So wherever her shoulders are at in the air, that distance from her shoulders to the water is given by the function y of t. And both of those are measured in meters. Suppose that the diver's shoulders are 11.4 meters above the water when she makes her leap. So I suppose this distance, even though it's not labeled in the picture, but this entire distance from her shoulders where she's starting to the edge of the water is 11.4. We're given her velocity x component, dx dt, which is 0.8. We're given her velocity y component, which is 3.6 minus 9.8 t. Part A wants us to find the maximum vertical distance from the water surface to the diver's shoulders. So of course the maximum distance that she's going to be away from the water is at the very top up here where I'm putting a dot, to the very top of her jump. Of course, after that she'll start falling and get closer to the water, but at the very top of that path, she'll be at a maximum vertical distance away from the water. And we want to find that distance. So again, we know that she's starting at 11.4 meters above the water. So we know her initial y position, y0, is 11.4. So we want to find the max height. So the one thing we know right now that can kind of get us to this answer is that the velocity in the y direction at the very top, the dot went away, but here it is again. The velocity in the y direction at the very top of her path is going to be 0. For that split second, she's going to stop in the air at the top of that path. And then, of course, she'll fall down to the water. So we know dy dt is equal to 0. So if we take that equation and set it equal to 0, I'm going to leave that as an exact answer. The reason I'm going to leave that as an exact answer is we never, ever, ever want to round until the very last answer that we're looking for. So unfortunately, we're going to have to leave that time when she's at her max height is 3.6 over 9.8. So that would have been really nice if this question had just said, at what time is she at her max height? But they're not asking us that. They're asking us what position she's at when she's furthest away from the water. So that's a position question. And if you recall from the last slide and the slide before that when we went over all the formulas and stuff, to find position, and in this case because we're looking at the y component, we need to integrate the dy dt from one time to another time. And the way you kind of figure out the times you're going to use is really just based on the times you're dealing with in a particular situation. They tell you the position at time 0 is 11.4. They tell you, or we just actually figured out, I should say, that the time when she's at her maximum height is 3.6 over 9.8. So we're going to integrate from 0 to 3.6 over 9.8 of our y velocity component. Of course, when we do that, that's going to equal the y position at 3.6 over 9.8 minus the y position at 0. And of course, we know the y position at 0 from above is 11.4. So really, it just comes down to taking your y component of velocity, which is 3.6 minus 9.8, and using the TI-89 to integrate that from 0 to 3.6 over 9.8. If you type that in the calculator, and it is worth noting, I hope you're pausing and making sure you're getting these values. Hopefully everything's working out in the TI-89. But if everything does work out okay, you should figure out that that value is 0.661224. Again, we don't want to round till the very end. After that, it's very straightforward. We can go ahead and add 11.4 to both sides, and then we're going to get a maximum vertical distance, or in other words, the y distance is 12.061 meters. Again, two very important things on the free response section of the test. rounding to 3 decimal places, and then not forgetting units. Okay, so continuing on with this problem, we're on part B now. What time does the diver's shoulders enter the water? So to do that, we would need to know what the position is in terms of y when she enters the water. And we know that that position is 0. So this question is really asking us to find the time when the y position is equal to 0. So it would be really nice if we already had the y equation, because then we would just set that equal to 0 so we could find that time. So what we're going to have to do is find that y equation. We know dy dt is equal to 3.6 minus 9.8t. So if we were to integrate that, that would take us back to the original y equation. So that's what we're going to do. We're going to separate the variables here by moving the dt to the other side, and then we can integrate both sides. Luckily, this is very straightforward. We'll end up with 3.6t, and then we'll take that t and add 1, which is 2, and divide by 2, so we'd have 9.8 over 2, or 4.9 t squared, and then definitely don't forget the plus c. To find the c, we're going to use the point they give us. Our initial y position, which is at 0, is 11.4. So if we take that and plug it in, you can quickly see the c is 11.4, and that is our y equation. So a little bit of work, but not too bad. And now we can answer the question that was posed. To find the time when y of t is equal to 0, we'll just set that y equation equal to 0. And again, the reason we're setting y equal to 0 is because that's the position when she enters the water. That time, if you use your TI-89, turns out to be negative 1.2 and positive 1.9. Of course, one of those answers is a little extra and it doesn't really apply to this problem. So of course, the correct answer here to 3 decimal places would be at time equals 1.936 seconds is when she enters the water. So it almost takes her 2 seconds to go from the platform jump down to the water. In part C, we want to know how far she traveled. We want to know what the total distance was from the time she leaps to the time that she enters the water. What was that total distance that she traveled? To do that, we need to use our arc length formula, or if you look at it from the point of view of these questions, the total distance formula. And that's just a matter of taking the dx dt and squaring it, taking the dy dt and squaring it, adding those two values, and taking the square root. And then within all that, we're going to integrate from 0 to the time she enters the water. So you can see part B plays a very important point in this part C. And on top of that, just notice we're not using the rounded off decimal of 1.936. We're using the entire set of decimals because, again, we can't round any of our values till the final answer. So just be very careful that you use all of those decimals in this part C. After that, it's all using your TI-89, and again, I would certainly pause and make sure you can get this answer so that you can just be confident in your calculator skills here. But if you enter all that correctly, you'll find that the total distance this diver traveled was 12.946 meters. In this last question, again, we're kind of concerned with what's happening right as she enters the water. We want to find the angle theta, and that angle theta is going to be between 0 and pi over 2, which makes sense. She's either going to enter the water perfectly vertical, but that's not possible really in a sense, or she'll enter the water perfectly flat, which means something really went wrong in the air. But of course, those are the two extreme cases. We're looking for the angle between 0 and pi over 2, or 90 degrees if that helps you, between the path of the diver in the water as she enters the water. We're looking for that angle as she enters the water. So to kind of help us out here, I'm going to draw a little picture here. This dashed line that you see is the diver. And I'm kind of, again, exaggerating the angle here. Of course, she's not going to enter at this angle, or something really went wrong in the air as she was trying to dive into the water. She's going to, of course, enter the angle a lot more vertical. But it's harder to draw that right triangle, so I'm drawing the angle a little more exaggerated so you can see what's going on here. So we're trying to find that angle theta at which she enters the water. So we know that there's two things at play here, again, because we're dealing with parametric equations. We know that we have her velocity in the x direction as one component to her entering the water, and we know we have her velocity in the y direction as one component to her entering the water. Just keeping in mind, though, that since she's falling towards the water, that distance is decreasing, so that's a negative rate of change, so negative dy dt. Again, we're looking for this angle that she's entering the water at. Again, I'm exaggerating this angle so we can see the right triangle a little bit better, but of course she's entering at a very steep angle. So then what is that angle going to be? Well, what we need to realize is from our basic trigonometry days, the thing that ties theta to the dy dt and to the dx dt is our trig ratio of tangent. We know tan theta is equal to negative dy dt, which is the opposite leg, over dx dt, which is the adjacent leg. And of course, we know those two values. Negative dy dt would be negative 3.6 minus 9.8t, and then dx dt is 0.8. After that, it's just a matter of using the TI-89 to plug in the value of t. We know the time that she enters the water at. We know the time that she enters the water is 1.936 seconds. But again, we can't use the 3 decimal round off. We need to use the entire set of decimals here. So we got to take that entire set of decimals and use that when we plug in. If we do that and evaluate that fraction at t equals 1.93626, we'll get 19.219185. And again, you have to keep all those decimal places. Okay, so again, some basic trig knowledge here. If we know tan theta is equal to a number, to find that angle, we need to arc tan both sides. Or if you are thinking of this in terms of the button you would press on your calculator, we would inverse tan both sides. So really, we're just taking the inverse tangent of 19.219185. And if you do that in your calculator, again, in radian mode, we'll find that she enters the water at a theta, or an angle, of 1.519, and it's not degrees here. We don't deal with degrees. We're dealing with radians.